Today's puzzle is based on a grid of tree heights. 0 is the smallest tree and 9 is the biggest tree. I started with a function that takes a string and converts it into a vector of numbers just because characters aren't comparable in Clojure with less than and friends. Okay, and we just use Java interop here. The character digit function takes a character and then a base. We want to convert from base 10. Then I have a parse grid function, which takes our example input here, splits it into lines as usual, and maps our string to digits functions from above to it. So then we should get a two-dimensional vector of numbers between 0 and 9. Then here's our good old friend, the transpose function again. It was a bit magical in the last video, but the purpose is to take basically a vector of lines here and then look at the columns and turn those into lines. And in case you're still not really clear how this works, take a look at the simplified example here. We map the vector over two individual arguments, and that works. Why does that work? So far we only mapped the function over one collection, but we can map it over as many collections as we want. So if we look at map_v, here is the arity that takes two collections, for example. So basically we call vector of 1 and 4, that's this guy, then vector of 2 and 5, that's this guy, then vector of 3 of 6, that's this guy. And if we don't have individual arguments, if we have a vector of those, then of course we need to apply everything as usual. And that's how this idiom works for transposing. Hopefully clearer now. Okay, then we want to determine if a tree is visible. For example, this tree with height 5 is visible if we go to the edge of the grid. All these trees are smaller, whereas this tree is not visible because here a tree has the same height. This tree is not visible because this tree has a bigger height, and this tree is not visible because this one has the same height. Okay, and we can almost literally translate the English into Clojure. So every one of our other trees has to be smaller than the given tree, where here via the structuring tree is the first guy in the list and the other trees are the rest in the list. So that's quite nice functional programming. Okay, and then for part 1, how many trees are visible from outside the grid? First, some let bindings. So we parse the grid, that was the function from above, and then we transpose the grid, swapping out the rows and the columns, so swapping out the meaning of x and y. That will become handy later. And then we see how long is the grid and how wide is the grid, just so we can iterate through both dimensions. Okay, and here we iterate through both dimensions. Y iterates through all the possible y values, x iterates through all the possible x values, and then we check if the tree is visible from at least one of these 4 directions. So what's going on here? So we take our grid at y, that's a row, and then we build a sub-vector starting at x inclusive and then going to the very end. So we scan to the right basically in our grid. Okay, and then if we want to scan to the left, we take everything from 0 to the increment of x exclusive, so everything from 0 to x inclusive, and we reverse that guy. So RC gives us a sequence in reverse. That's why we look to the left now instead of the right. And then for the other two directions, basically we copy pasted the right and the left code, but we exchanged the grid to Dirk, and then x and y change meaning. So right then becomes down and left then becomes up. That's why we transposed the grid. And it doesn't really matter which value we pick here. We're only interested in the count. Right, then next guy, the viewing distance. So here the viewing distance from the 5 tree to the border is 1 because we can see this tree. Then here it's also 1 because we stop at the first tree that is equal. Here it's 2 because we see both trees. And here it's 2 because we can see the smaller tree and the equal tree, and then we stop. So we have to be a bit careful. Is our view blocked by a tree or is it blocked by the edge of the grid basically? Okay, and we do structure again. And then we use the take while function. We want all the other trees that are smaller than our tree again. So in our case here, that would be, for example, 3. Here it would be an empty collection. Here it would be these 2 guys. And here it would be the 3. Okay. Yeah, and then there's basically 2 cases. So my first instinct was to say I simply count the smaller trees, for example here, and then then simply add 1 to it because we were blocked by the next guy, and the next guy shall be included by the result, but take while will not include it. So it's not a take until, it's a take while. So I want to account for that additional tree with the inc function. But of course, if we weren't blocked by a tree, but by the grid, for example, here, I don't see 2 trees here. I only see a single tree. So in that case, I won't count other trees, and I simply pick the minimum of those. So only in the cases where I can see to the very edge, I don't really want to increment. That wouldn't make sense, and the min will catch that. Right, and then for part 2, the format is quite similar to part 1, mostly copy-paste. But here, this is different. So now we compute the viewing distance in all 4 directions. So that's basically the same, just swapped out for a different function here. The rest is exactly the same. And here we multiply them instead of filtering with an OR. So multiply all the viewing distances, and then we don't want to count anything. We want to find the maximum. So I simply reduce by max starting at 0. So every other value that's bigger at 0 will replace the 0. Yeah, and that's already everything. So I think quite a nice functional solution. Lots of functions and no manual tedious array indexing and bounds checking.